Okay, can you see my screen?
Yes.
Good. Okay. Great. Okay. Thank you. Thank you, everybody, for attending my talk. And thanks for the organizing committee for inviting me to speak about particle acceleration in jets. Today, I'm going to talk about this numerical code that I've been working with for a couple of years. And the structure of my talk is the following. So I will be giving a brief introduction and motivation for the developing of the code. Then I will talk about the main features. I will move on with the astrophysical application of the code, and then I will end up with a summary and a conclusion. So first of all, I want to thank Woody for this great overview in the morning around relativistic jets. So I'm gonna skip all those details, and I will move on with the what are like about to talk about the gamma ray bursts. So gamma ray bursts are these high energy and highly energetic events that come into flavors, mostly long and short, depending on the progenitor. And these events have two main phases. The first one is the prompt phase, where most of the energy is released after the outburst of the jet. And as the jet moves on and it starts interacting with the circumburst medium, we enter into what is called the afterglow phase. In the afterglow phase, there is the consensus that particles are being accelerated by this shock that is formed after this relativistic jet starts propagating outwards. And these particles, these electrons, accelerated electrons, interact with the magnetic field of the jet, producing synchrotron photons. And these same synchrotron photons interact with the same accelerated particles, producing a high energy bump through the process of inverse Compton, called the synchrotron self-Compton. And this process gives a lot of there is a lot of energy deposition between particles and photons and back and forth. So these kind of processes were like main motivation to start working on this code with these two main ingredients. So okay, let's talk about these ingredients for the to account for this these spectra that we observe in relativistic jets. Okay, so the first ingredient are the particles, the accelerated particles. So to model the accelerated particles in relativistic jets, we can do that considering the kinetic equation, better known as the Fokker-Planck equation. So in the code that I developed, I solved the full Fokker-Planck equation with a sophisticated numerical solver, taking into account, well, in the code we can take into account the diffusion processes, the energy diffusion processes, energy gains and losses. We can also include source terms and escape of particles. So here, for instance, we have a simple test for the solver, in which we can see how distribution evolves and reaches the steady state. And if we turn on the injection and escape of particles, we can see a completely different evolution, but also reaching the steady state profile. But as particles escape the system, we lose them. Okay, so this is the first ingredient for what we want to achieve. Yeah, we want to achieve simulating a dynamical distribution of particles, which is what we have in relativistic jets. So this kinetic equation will give us that that part of the for the particles. And for photons, a series of numerical, sophisticated numerical techniques have been developed some time ago to be able to simulate or to calculate the synchrotron self-absorption, and inverse Compton scattering for an arbitrary distribution of particles, not only a power law, but a dynamical, not so simple distribution of particles. And these numerical techniques, I included those techniques in this code that I named Paramo, by the way, so that we were able to get all these dynamic spectral evolution. But to get this dynamical spectral evolution, I implemented two ways of doing that. One through the radiative transfer equation, and the other one by using the Kompanitz equation. So this code is capable of doing this, calculating the photon fields in both ways. Why is that? Because each of one has its own advantages. For instance, the Kompanitz equations has the advantage that you can account for all, you can conserve the number of photons. Okay, so that is, and also you can account for for instance, if you have a pair creation and all that stuff, you can solve this coupled system of equation. And also something that I missed to mention is that with here I didn't specify that this is only for electrons, but you can also this can also be used for different species of particles. So by coupling these equations, one can start evolving different distribution of particles, including photons, or we can calculate each component of the spectra using the radiative transfer equation. Okay, so one of the most important, or the main motivations of keep going developing this code was this interaction between photons and particles, mainly how the photons extract the energy from our distribution of particles through the inverse Compton. So this is a very complicated process. If one reaches this limit, so okay, briefly, I'm gonna step back a bit. Inverse Compton is this scattering process in which highly energetic electron scatters a low frequency photon into a highly energetic photon. So this extraction, or this transferring of energy from the particle to the photon will be efficient or not, depending in which regime it is. So if one reaches the Klein-Schiene regime, this the extraction or the transferring of energy will be different, because the cross section will be different. And I didn't stop to show the whole Klein-Schiene cross section because it's nuts, and I don't have that much time. But moving on with what I want to show you is that I developed this numerical technique to actually calculate the Klein-Ishina cooling, well, the inverse Compton cooling, those radiative cooling, taking into account the Klein-Ishina corrections numerically. Why numerically? Because as I said, this is a very complicated calculation to do, and so I made this numerical way of doing it a bit more efficiently. And here I compare the numerical calculation of the Klein-Ishina, the radiative cooling, comparing it with analytic Klein-Ishina approximation for a black body, and for the Thomson Thomson regime. As we can see, the numerical approximation pairs quite smoothly between the two regimes, and performs the same way with a monochromatic incoming photon field. Yeah, that's something that I wanted to achieve with these numerical techniques, is that I wanted to calculate the radiative cooling for an arbitrary incoming photon field. So that is something that it's novel for the to calculate the radiative cooling. Okay, so something that I have to mention here is, as we can see, the Thomson regime is very efficient. It cools photons very efficiently, while the Klein-Ishina, as you move into a higher highly energetic photons, it gets less efficient. Okay, so for the astrophysical application of this code, I picked a simple firewall model of a GRB, taking the analytic solution for the blast wave, and in a homogeneous external medium. I inject a power law distribution of particles, and I make the proper transformation between the different reference frames, and let the things evolve, let the particles evolve and start to do their thing. For the initial condition of the blast wave, I picked the case of the GRB, the magic GRB. And why did I pick this GRB in particular? Because it is the observations were like all over to the TeVs, which means that this is a perfect scenario to test those the Klein-Ishina regime. So I picked that object, and I also picked monochromatic incoming field. So a monochromatic incoming photon fields, plus the synchrotron photons that were produced in situ. And I let the system evolve, and what I get is something very interesting that was also expected to happen. As I said before, the Thomson, okay, yeah, here in this plot, what we can see is the particle distribution evolving along with the light curves and the spectral energy distributions of the system. In the solid lines, we can see the the evolution considering only the Thomson regime, while the dashed lines correspond to the same configuration, but the cooling is considering the Klein-Ishina corrections. So as I was mentioning, the Thomson cooling, Thomson cooling is very efficient, but if we consider the Klein-Ishina corrections, particles won't be cooling that efficiently, and that's why we have this piling up of electrons, because particles will be injecting. We have a continuous injection, as we mentioned. We saw here in this test. The particles keep are being injected constantly, and so we have that, and particles start piling up because they are not being efficiently cooled. If we consider the Klein-Ishina corrections. And this is translated into the light curves as a in the same in this so in light curves we can see a significant difference between the two cases in the high energy bands. Here, for instance, we have in the green line we have the Fermi-LAT band and the MAGIC band and the X-rays, and they have a significant difference, while in the at low frequencies there is none, because for those cases we the low energy particles are not that different. Okay, so I want to come to a summary. Scott, am I on time?
Well, yeah, there's no time for questions, but
okay, sorry. Okay, yeah, so I want to just to summarize this, that this code is not only useful for a simple blast wave, it is being set up for structured jets, and this structured jet could be by solving the system of equations of for the blast wave, and also for considering a simulation, jet simulation. This code can be adapted and into those numerical into a numerical jet simulation, and calculate the emission in for instance in a shock, where the shock are in the simulation. Okay, that is work in progress. Thank you.
Great.